So I'm over here in the projectile motion slide, and you can see there is a human cannonball type situation. This is part of the reason why I love projectile motion, because I mean it's studying the motion of things flying through the air, which is just kind of fun, right? Especially when it happens to be a human being being shot from a cannon into a net. So projectile motion is just like kinematics, except you have to worry about two things now, right? Any object undergoing projectile motion it's moving in two dimensions. So let's be a man shot out of a cannonball. So let's say this is my cannon, right? And this is the human being, right? And let's say he is now shot out of this cannonball. And he forms a perfectly parabolic arc, okay? That's the first thing to know about projectile motion, that if you neglect air resistance, all objects in projectile motion move in a parabolic arc, a perfect little parabola, upside down parabola, okay? And which is quadratic. It's a quadratic function. And you'll see why that is a little bit later. So because now I have some motion happening in the y dimension, right, up and down, and I have some motion happening here in the x dimension, right? Now we need two laundry lists to solve these problems. Okay, so that's number one. And we have to be very, very careful to separate the variables in the two dimensions. You can never use anything in the x dimension to solve for something in y, and you can never use anything in y to solve for something for x, except for one thing. See if you can think about it. What would be the one variable that's okay to use in both dimensions? The answer is time, okay? Reason being, because obviously however long it takes you to get to here in x is the same amount of time it takes you to get up to that point in the y dimension, because, I mean, your body's not separating the two different times, right? So time will be the constant, the one thing that's the same between the two dimensions. But we're going to explore that more later, okay? So if you go on to the next slide, it says the components, okay? And so I want to analyze this very, very carefully so that you see exactly what's happening to the components of velocity as an object moves through this parabolic arc, okay? And I feel like once you really kind of have an understanding of what's going on with the components of velocity, the problem becomes a little bit easier, okay? So here's what's happening, okay? At the very, very beginning, right, this guy's shot out with some velocity v, right? Okay. As you can see, there's going to be an x component of that velocity, and there's going to be a y component of that velocity. Okay? Very, very important that you see the difference between those, and that you notice that there is some angle that it's being shot at, right? And just like you know from the last chapter, from the vector work that we've done, this Vx component is just going to be the initial velocity with which it was shot, v, times cosine of this direction, right? Just that guy, right? And Vy, of course, will just be v sine theta, okay? So probably the very first thing you should do whenever you're solving a projectile motion problem is to find those two components if that's possible. Find your Vx component by taking the velocity that you're being shot with times cosine theta, and find your y component by taking the velocity that's shot with times sine of the angle or the direction that it's being shot at. Okay? So what about when the guy's over here? What's happening, right? Well, here's the thing. Vx never changes because there's no acceleration in the x direction, right? So velocity shouldn't change. So our Vx stays the same throughout this entire journey, right? He does not change whatsoever, okay? In fact, even up here, Vx is still the same Vx. They're not perfectly the same length, but I'm trying to make those the same length. Here, it's still, Vx still the same. And here, just before it lands, it's still the same Vx, right? Not true for Vy, okay? For Vy, the velocity is always changing because of 3, 2, 1. gravity, right? So in other words, gravity is slowing this component down, so here the Vy component will be a little bit less, okay? All right, and so up here, so this is our Vy, at the very, very top, gravity has slowed the Vy component all the way to 0, right? If it didn't, then what would that mean? It would mean that it could keep going up farther. So at the very peak, at the maximum height, Vy here is just 0, the Vy component. So you only have the x component of the velocity left, right? Now, what is gravity doing? Well, it's accelerating this guy downward. So now I have now a negative Vy component, right? That's still not as big as I originally had it, right? And over here, just before you hit the ground, you have a negative Vy component that has to be equal to the initial Vy that it was shot at, right? If this guy launches and lands at the same height, okay, the Vy component positive here must equal the Vy component here negative, right? So in other words, the magnitude of your initial Vy must equal the magnitude of your final Vy, right? Although this will be negative, okay? And the reason for that is symmetry, right? If gravity is slowing it down for exactly this long, right, then gravity is going to be accelerating it downwards for exactly that same amount of time. So these have to be equal. When we learn about energy, you're going to find out that according to conservation of energy, the velocity here should also equal the velocity there, right? Unless it's somehow lost or gained energy over the journey, right? But in this case, that's not happening. Okay, so take a look at this. Make sure you really understand it. What I want, the biggest things I want you to take away from this is that Vx stays the same the entire time because acceleration in the x direction is 0, and Vy is constantly changing. First, it's getting smaller, and then Vy is getting bigger just before it lands, at which point the negative Vy is equal to the positive Vy that you started with. Okay? So on the next slide, I have another way of kind of expressing this and showing this with the delivery of a care package. Here you can see, again, the Vx component stays the same everywhere on that path as the care package is falling, right? Vx component staying the same at 115 meters per second. But I'll just draw it right here, right? So you get this plane, right? And it's dropping off this care package. And so the Vy component, there's a Vx component here, but the Vy component is 0. Here, Vx component is the same, but Vy component gets a little bit bigger. And then here, Vx component, again, stays the same, but Vy is even bigger, right? Because gravity is accelerating it downwards. All right? So just, again, notice how the x component of the velocity stays constant, while the y component steadily increases due to gravity. Okay. The next slide is misconception question number 1. What's that? Number 1. Okay. The baseball player is hitting the ball that soars high into the air. After the ball has left the bat and while it is traveling upward, what is the direction of the acceleration? Okay. This is one of the easiest places that students get tricked up, right? They think if they hit a ball, right, or a soccer ball, or kicking a soccer ball, or basically anything that causes something to fly in the air and doing projectile motion, that the force stays with the object. But that's not true. As soon as you hit the bat, right, or hit the ball, there's no more force from the bat on the ball once it's flying in the air, right? There's only one force the entire way acting on that ball. What would be that force? That force would be gravity. And so in other words, the direction of acceleration is always the same as the direction of the force. So the answer would be B. The only acceleration acting on that ball is gravity's downward acceleration at every single moment in time. Okay? You would not hit, so if I'm like, let's say, here's the bat, right, and I'm hitting the ball here, right? Once the ball's here, so at that very instant, there's a force being applied to that ball, right? There's a force being applied to that ball right now when it's in contact, right? But the second it leaves contact, there's no more force on the bat. So here, there will not be a force in this direction. There's only going to be the downward force due to gravity. Okay? I hope that's clear. And in the next video, we are going to be starting to do some practice problems involving projectile motion. And I'll see you in those videos.